In the vastness of our solar system, the Sun, a constant powerhouse of nuclear energy, occasionally exhibits dramatic bursts of activity known as solar flares. These intense explosions on the Sun's surface release vast amounts of energy, equivalent to millions of 100-megaton hydrogen bombs exploding at the same time. Solar flares are associated with magnetic field disturbances on the Sun's surface, which propel a tremendous amount of solar radiation across the electromagnetic spectrum. As these charged particles are ejected from the Sun, a phenomenon known as a coronal mass ejection, or CME, can occur simultaneously. This powerful event sends billions of tons of solar particles hurtling through space at speeds up to several million miles per hour. When directed towards Earth, these particles can reach our planet within a matter of days. Upon their arrival, these solar particles collide with Earth's magnetosphere, the protective bubble of magnetic fields surrounding our planet. This collision causes complex changes in the magnetosphere, triggering auroras, commonly known as northern or southern lights, which illuminate the sky with breathtaking colors. Modern scientific instruments stationed on satellites in space monitor these solar events closely. They provide crucial data to predict when these cosmic storms might strike Earth, allowing for timely warnings about potential disruptions to satellite communications, power grids, and even impacting Earth's climate systems. As the massive solar flare's energy penetrates Earth's magnetic shield, the first noticeable change is a sharp increase in the upper atmosphere's temperature. This sudden heat surge is not evenly distributed across the globe, creating pockets of superheated air that begin to disrupt normal atmospheric patterns. The influx of extraordinary solar radiation directly heats the atmosphere, leading to rapid temperature increases. Such conditions are particularly pronounced in Earth's ionosphere, where the interaction with charged solar particles heats and expands the atmospheric gases. Back on the surface, the effects become increasingly evident as the heightened temperatures lead to accelerated evaporation rates of Earth's water bodies. Lakes, rivers, and oceans release vast amounts of water vapor into the air, saturating the atmosphere at an unprecedented rate. In populated areas, the spike in temperatures can be felt almost immediately, with days becoming hotter, leading to uncomfortable and even dangerous living conditions. Urban areas, with their extensive asphalt and concrete, become urban heat islands, exacerbating the local effects of the global temperature increase. As the heated and moisture-laden air rises, it disrupts the stability of the existing weather patterns. The warm, moist air ascends into the cooler upper atmosphere, leading to the formation of dense, voluminous clouds. These are not ordinary clouds. They are thicker, more extensive, and carry far more moisture, setting the stage for extreme weather events. As the atmosphere grows increasingly unstable with the buildup of heat and moisture, it reaches a critical threshold. The dense clouds, heavy and swollen with water vapor, begin to merge and spread, covering vast areas of the sky. This phenomenon is not localized. It spans continents, driven by the altered global air currents that push these supercharged clouds far and wide. Initial light drizzles soon escalate into relentless downpours. The rain, once a nourishing element for the Earth, now turns into an unyielding deluge. Across the globe, regions experience continuous heavy rainfall, the likes of which are rarely seen outside of the most severe tropical storms. The ground, unable to absorb water as quickly as it arrives, succumbs to the inevitable. Rivers and lakes, swollen from the rapid runoff, begin to breach their banks. Urban drainage systems, overwhelmed by the volume and persistence of the water, fail to channel the floodwaters effectively, leading to widespread urban flooding. In rural areas, fields become lakes, and crops are submerged under swift, muddy waters. The agricultural damage mounts as floodwaters wash away fertile topsoil, leaving behind sediment and debris. The essential food production regions face catastrophic impacts threatening food security. Natural reserves and forests are not spared. Water courses through previously dry creek beds and low-lying areas, reshaping landscapes and altering ecosystems. The flooding disrupts wildlife habitats, forcing animals to flee or adapt quickly to their rapidly changing environment. As the monumental solar flare's influence wanes, Earth's atmosphere begins a gradual process of stabilization. The supercharged clouds that once dominated the skies start to dissipate, and the relentless downpours reduce to gentle rains before ceasing entirely. This marks the beginning of a significant drying phase where waters recede, and the saturated earth starts to firm up. The swollen rivers that surged beyond their banks begin to retreat to their natural channels. Lakes and temporary floodplains drain, gradually exposing land that had been submerged underwater for weeks. The natural drainage of these vast water bodies restores balance to the hydrological cycle, crucial for maintaining the ecological equilibrium of the affected regions. In the aftermath, the once inundated lands reveal a changed landscape. The floodwaters, though initially destructive, leave behind nutrient-rich sediments that enrich the soil. As the ground dries, vegetation starts to reclaim the terrain, sprouting vigorously, fueled by the newly deposited nutrients and increased soil moisture levels. Evaporation rates escalate as the sun's rays warm the earth, creating a more humid atmosphere than before. This increased humidity plays a key role in stabilizing the temperature across different regions, gradually restoring the disrupted weather patterns to a new state of equilibrium. As we witness the resilience of Earth, it becomes evident that despite facing extreme disturbances, our planet possesses a remarkable ability to stabilize. The immense solar flare, with its cascading effects of heat, storms, and floods, tested the limits of Earth's environmental systems. Yet, over time, the natural processes inherent to our world worked in concert to restore balance. Through the cycles of evaporation, condensation, and precipitation, the atmosphere cleansed itself, and the land absorbed the excess moisture, rebalancing the climate. This intrinsic ability to heal and find equilibrium, even after significant disruption, underscores the dynamic and self-regulating nature of Earth. Throughout its history, Earth has demonstrated time and again its capacity to push back against disruptions, whether natural or human-made. It continuously seeks a state of equilibrium, a balance that allows life in all its diversity to flourish. This dynamic self-regulation is a powerful reminder of the planet's enduring stability.